All right, here the recording in progress. Right now it doesn't look like you can see me, but you probably don't want to see me anyway, so it's no big deal. Try to share the screen here. Okay. So I think we're good. Right here. Okay, so we're up to here. Our next exam is this coming Friday already. So we had our quiz. Should have emailed you back your quiz result. If you did not get your quiz result from me, then let me know, send me an email. Quizzes are out of 5, so you got a 5, 4, 3, 2, 1, or 0 on the quiz. By the way, reminder, even though I don't take attendance formally, if you miss 4 quiz/exams combined, I might drop you from the course. That's what I consider as excessive absences. So excessive absences for me means you miss 2 quizzes and 2 tests, or 3 quizzes and 1 test. It means you've disappeared essentially. And so that's my definition of excessive absences. Okay. So you've already gotten that back, and I sent out the video, the solutions video over the weekend also. So you should be good for that too. Okay. We're not having a quiz this coming Friday though, because we're having a test. Right. So reminder, exam 2. Now that we've already had 1 exam, you know what all the exams are like. So you submit the homework starting on Thursday after class. I'll start taking the homework. It's just 2.2 to 2.5. And recall for 2.2, we're skipping 37 and 15. Okay. And there's a 70% homework requirement, but that's pretty easy to do considering I do a whole lot of the homework anyway. And sometimes I almost literally do 100% of the homework or very close to it, in which case all you have to do is copy it. Okay. And again, attendance is required for this. So I know I say you don't have to show up in general for the lectures because you can always look at the videos, but not for the exams. The exams you have to show up synchronously with your camera on, true background, keep yourself muted, good stuff like that. And you have to submit at least 70% of the homework. As I said, that's pretty easy to do. I tend to give about 10 questions in the test, so looks like we only had 4 sections, so there'll be, I guess, 2 questions from every section and maybe a couple more from some other section, but about 10 questions, just like last time. Okay, so I'll send the exam over Canvas announcements around 9 o'clock, 9:01, 9:02, something like that. You will show up. I will take attendance. Again, have your camera on, keep yourself muted, have the true background, and during the test, if you have any questions, put it in the chat. I'll close the Zoom session at a normal stopping time of 10 o'clock. And then I'll give you until 10:05 to take pictures on your cell phone, just like the quiz. And then you have until 10:30 to submit the homework. Although, if you want to submit the homework early, like right after class on Thursday, then, get it over with, then you can do it that way also. Okay, but now you've seen 1 exam, what, all the exams are going to be the same style. Okay. It looks like chapter 4 is our longest chapter, and that's because it's trig. This is a review of trig. Okay. The other, this was a pretty short chapter, and it looks like at the end we have some pretty short chapters also. Okay, that's where we're at. Okay, so schedule-wise, we were just about to finish 2.4. So 2.4, a couple of days in 2.5. Thursday, buffer day, meaning you can ask questions, or if not, I'll just start the next chapter, sneak in some of chapter 2. And so the next exam is on Friday, this coming Friday, the 17th. Okay. All right, so any quick questions about that, please? And I just wanted to warn you, it's pretty noisy outside my home right now. They're doing some construction. So if you try to unmute yourself, I probably can't hear you. So you may have to put something in the chat. I guess that's another drawback or another result of teaching online, that we're home and we're not on campus, but if we're home, then if they do something weird like construction outside, then maybe I can't hear you so well. So if you have a question, put it in the chat now. Any questions about what's going on, please? Okay, so let me get back to 2.4, maybe knock it off and go from there. All right, so back to this composition of function stuff. Question 19. H of x is 1 over x plus 2. Find functions f and g such that h equals f circle g, f of g of x. Okay, now g is the inside function, f is the outside function. So you just have to break it down that way. So it's like one function is the reciprocal function, and the other function is adding 2. So a simple solution would be let f of x equal 1 over x, g of x equal x plus 2. Okay, so fog, f circle g of x is f of g of x, which is f of x plus 2, and f of x plus 2 is 1 over x plus 2. So that's all you have to do. Okay, and I'll speculate. Suppose we reversed it. I mean, the only thing you would guess is you look at the original problem. There's a reciprocal, it's 1 over something, and there's also x plus 2, right? So you say, which one is it? Well, what happens if I reversed it? Suppose I said f of x is x plus 2, g of x is 1 over x. Then f circle g of x, f of g of x would be f of this, which is 1 over x. And f of 1 over x means whatever's behind my pen, I add 2. So it's 1 over x plus 2, but you may notice that's not equivalent to the original. Okay, if I clean this up a little bit, 1 over x plus 2, 1 over x plus 2 over 1, common denominator is x, multiplied top and bottom by x. You have 1 plus 2x over x. That's not the same thing as 1 over x plus 2. Okay, so that's that one. Okay, and 15, something sort of similar. H of x is 3x squared minus 2 to the 4th power. So one function is raising something to the 4th power, and the other function is 3x squared minus 2. Inside, outside. So the outside function is your f. So f of x is equal to x to the 4th. G of x, 3x squared minus 2. Okay, so again, outside function is raising something to the 4th power. So that's going to be my f. Inside function is my g, because it's f circle g. And you can double check that. Fog, right? F circle g of x, f of g of x. But what is g of x? G of x is 3x squared minus 2. So I'm doing f of 3x squared minus 2. And what does f do? F raises whatever you give it to the 4th power. So it's whatever's behind my finger to the 4th power. So 3x squared minus 2 to the 4th power. And that's exactly what we wanted for problem 15, right? 3 squared minus 2 to the 4th power. Now, with that background, I'm on 17. And yes, I would have literally done all the problems, but I'm sure you don't mind. Cube root x minus 4. So f is your outside function, f circle g. So the outside function is the cube root function, right? So how do you know? Well, by order of operations, right? If you see this expression, cube root of x minus 4, and you plug in something, suppose I say plug in 5. Okay. From this expression, are you supposed to do the cube root first, or do you subtract first? If I say plug in 5, you would subtract first, right? 5 minus 4 is 1. Then you do the cube root of 1. So that tells me the inside function is x minus 4. outside function is cube root. So that's going to be my f. So h of x is cube root of x minus 4. So I said the outside function is the cube root function. F of x is cube root of x. Inside function, g of x is x minus 4. And a quick double check of that. What is the fog, f circle g of x, f of g of x? What is g of x? So leave the f alone, leave the left paren alone, leave the right paren alone. In place of g of x, I put down x minus 4. So I'm doing f of x minus 4. And now what does the f function do? F takes the cube root. So f of x minus 4, cube root of x minus 4, done. Okay. All right, so that's that one. Was asked to go back over 13 again, so let me rehash 13. It's a little bit tricky with all the reciprocals. F of x is 1 over x, g of x is 1 over x plus 1. And they want f circle g, they want g circle f, and give the domain of each composition. Okay. So let me go back over that one again. All right, so fog f circle g of x means f of g of x. Leave the f alone. Leave the left and right parentheses alone. F, left paren, right paren. Now, instead of writing g, I write down what it's equal to. What is it equal to? 1 over x plus 1. And now that thing goes right there. So it's 1 over whatever's behind my pen. Okay, so see the right here, 1 over. I write the 1 over, and now behind that pen, 1 over x plus 1 goes right there. I know it's weird, you got a fraction inside a fraction, but if you just faithfully say 1 over x, I copy the 1, I copy the fraction, and now whatever is behind my pen, be it easy or hard, goes right in the bottom. So there it is, 1 over x plus 1. So I have 1 over x plus 1. But remember, that means multiplied by the reciprocal. If you divide by a fraction, multiply by the reciprocal. So I changed it to 1 times x plus 1 over 1. So the answer is just x plus 1. Domain. If you just only look at this, you might say all real numbers. That's not the way this function works. It's officially f circle g of x. And for g of x, I'm not allowed to plug in -1. So -1 is no good. So the domain is all real numbers except for -1. Okay, so it has to go this way.
So you know, in the text, when I read it, it didn't really say specifically that you don't include what the original equations don't include. So when you're doing like f plus g, f minus g, f divided by g, and also f with g, you include everything from the original equation to the resulting equation. I mean, what all of these equations include and don't include.
Yeah, it kind of depends. I think I heard you, but if I didn't get you, Bonnie, let me know, because I got maybe 3/4 of what you said between all the noise outside. But I think you were saying if you're combining them and so on. So right here, when I'm doing f of g, right? So 1 over x plus 1, I cannot plug in -1 right here. I'm not allowed to. So even though your final result came out to be x plus 1, which originally you would say the domain is all real numbers, but officially, I'm really doing f of g of x, and g of x cannot allow -1. right? I'm doing f of g of x. So -1 doesn't get me past the first gate, so to speak. It's almost like there's two security gates. You got one security gate for G, another security gate for F. That first security gate you can't get past if you're plugging in -1. So you can't even get through there, so to speak. Even though -1 is allowed, where -1 is not allowed here. Yeah, you might say -1 is allowed here, but that doesn't matter, right? You can't get past that first security gate, so to speak, of having -1 here. So the domain remains all real numbers minus a set consisting of -1. Okay. All right, now, G circle F, which was a little bit harder. G circle F means G of f of x. So order of operations, do the inside. So copy the G, the left paren, and right paren. So there we go. G, left paren, right paren. Now, behind my pen, replace f of x with what it's equal to. Right? So what is it equal to? Look back up at the top, right? 1 over x. So G of 1 over x.
Really quickly, going back to the first part of the equation, part 1, f of g, why is 0 included since 1 over x can't be, why isn't 0 not included? Because 1 over x cannot be 0. I mean, x cannot be 0 and 1 over x.
Right, so how come x is in the domain? It's because I'm not really plugging in 0 here. I wait until I see what happens here. Because I'm doing f of g of x, or let's just actually say, what happens when I plug in 0? Okay, let's actually do it. You apply it over here, right? So 1 over 0 plus 1, that's allowed. You get 1. And then I plug in here, 1 over 1 is 1. So 0 is allowed. Because I'm doing f of g. Now, if I'm doing g of f, then it would not be allowed, which I'm about to look at. So I claim 0 is not in the domain of Goff, G circle f. It is allowed in the domain of f circle g. Because when I say plug in x is 0, you don't plug in here first, right? When I do f of g, the rules of the game say put 0 here. And when I plug in 0, this thing gets transformed to 1. So when I plug in 1, now I'm okay. So we're actually going to be good. Because I'm not plugging in 0 here, I'm plugging in 0 here, that transforms to 1. And then when I plug in 1 here, I'm good. So 0 is in the domain of f circle g, but it's not going to be in the domain of g circle f, for sure. Okay. Yeah, I think I heard you there because you seemed to stop construction for a moment. So I think we're good there. Okay, speaking of Goff, G circle F. So again, it's G of f of x. So let's see, where was I? Yeah, right here, right? G of 1 over x. So G of 1 over x. So whatever it's behind my pen right here goes right over there. 1 over something plus 1. So here's the skeleton. 1 over something plus 1. And what is the something? 1 over x. So there we go. 1 over x plus 1. And yes, right here, 0 is not allowed. So for Goff, G circle F, 0 is not allowed. And there may be more that's not allowed. In fact, there will be one more. Okay, this is technically correct, but you shouldn't leave your answer like that. Multiply top and bottom by x to clean it up. X over 1 plus x. Aha, -1's not allowed here. 0 is not allowed here. Right, so the domain is all real numbers minus the set consisting of -1 and 0. Okay, so officially, this is my Goff G circle F, right? That's what I have there. And I just double check, right? You're not allowed to plug in 0 right there. You're not allowed to plug in -1, because if I plug in -1, I get 1 over -1, which is -1, and -1 plus 1 is 0. So that would make this whole thing 0, and that's a no-no also. So that makes the domain all real numbers minus the set consisting of -1 and 0. Okay. So that's that. Okay. Okay, that's it for that. Now, 21 requires you to look at the picture. So, unfortunately, the only way I can do that is to go like this. Use the graphs of f and g to evaluate each expression. Okay, so how do I do that? And the noise just picked up a lot again outside. So if you're trying to say something to me, there's no way I can hear you. Sorry. F circle g of -2. Yeah, maybe I can go like this. F circle g of -2 means f of g of -2. So first g of -2. G is the red graph. F is the blue graph. So g of -2. Whoops. So 1, 2, red graph 1, right? F of g of -2. G of -2 I'm claiming is 1. So again, you do the inside first. G of -2 is 1, right? When x is -2, y is 1 for the red graph. Now I want f of 1, which means when x is 1, give me y for the blue graph. So blue graph, when x is 1, y is 2. So the answer is 2. You guys okay with that? So there's no computation, it's just looking at the picture. Okay, so one more time, f of g of -2. So you want g of -2. So red graph, when x is -2, y is 1. So this thing right here behind my pen right now, I replace it with 1. Now I do f of 1. So x is 1. What is y for the blue graph? And now it's 2. Okay. A little bit tricky how these things work. Okay. 2. G circle f of -2. Goff of -2. This means g of f of -2. So first I do the inside, cover this up. What is f of -2? So f is the blue graph. So look at the blue graph, ignore the red graph. When x is -2, what's y? So 1, 2, where am I? Right here, 0. F of -2, blue graph. When x is -2, y is 0. It's right there. So the next step, I replace that f of -2 stuff with 0. And now I want g of 0. All right, g is the red graph. So red graph, when x is 0, y is 0. The two graphs touch right there, but that's immaterial. You guys okay with that? Okay, so one more time. First, I do f of -2. So when x is -2, blue graph, y is 0. Then I do g of 0. G of 0 is 0. Three, G circle F of 2, golf of 2, and fog of 2. G circle F of 2. All right. G circle F of 2 means G of F of 2. So first I do F of 2. F of 2, red graph. Sorry, blue graph, messed up. F is the blue one. Blue graph, when x is 2, what's y? 0. Okay, so right there is 0. So now I want g of 0. G of 0. I just did that. 0. That's also 0. Okay, and 4. F circle G of 2. Fog of 2. It means F of G of 2. F of G of 2. So G is the red graph. So red graph, when x is 2, red graph, x is 2, y is -1. So that means inside the parentheses, I want -1. Now what do I want? F of -1. F of -1, blue graph. Blue graph. Y is -2. Okay. A little bit tricky. Part B. Determine all values of x that satisfy the equation F circle G of x equals 0, G circle F of x equals 0. How do you do that? Well, for the first part, fog, that means you want F of G of x equals 0. Okay. F of what gives me 0? We actually did that in the first part. F of what gives me 0? Well, we know that whenever the G came out to be 0, I end up with 0. In the previous part, that happened at -2, 0, and 2. Okay. So in other words, this gets a little bit tricky. So I say to myself, behind the pen, if I had -2, 0, or 2, I would get the answer to be 0. Behind my pen, G of x is -2, 0, or 2. But just think of a new problem. F of what number is 0? F of what number is 0? -2, 0, and 2. So now I say to myself, how do I get the thing behind my pen to be -2, 0, or 2? F of what number gives me -2, 0, or 2? So let's see. F of what number gives me -2, oops, -2, 0, or 2? Okay, I have 4, 0, and -4, and let's see why. When x is 4, y is -2. That's correct. And 0, 0. And I'm going to say -4 because by the pattern here, it's 1, 2, 3, 4, 1, 2, 3, 4. Okay. So x is 4, 0, or -4. That's what I want for that.
What number is this?
I'm doing 21 BI. Whoops. Just focused here. Come on. So 21 BI, I'm saying is 4, 0, -4. And now II, so 27 B2. Hard to say all this stuff. G circle f of x is 0. That says G of f of x equals 0. All right, so I look at my pen. G of what number is 0? G of, whoops. G of what number is 0? Only 0. So I will get a true statement if behind my pen is equal to 0. That means f of x equals 0. Where is f of x equal to 0, i.e. y is equal to 0 for the f graph? For the blue graph, where is y 0? -2, 0, and 2. And the answer is -2, 0, 2. A little bit weird. It looks like that's what we got. Okay. Finally, 23. I'm not going to emphasize it that much. We'll do a lot more of this when we get to the trig. But horizontal compression and elongation of graphs, page 108. Okay, so you may put this on your cheat sheet if you wish, but I'm not really going to emphasize it too much. For c greater than 1, the graph of y equals f of c of x is a horizontal compression. And for 0 less than c less than 1, a horizontal elongation of the graph y equals f of x. See figure 7a. Page 107. Okay, it's kind of hard to see what's going on here, but the blue is the original function. So you can kind of get around the colors. Only look at the blue. I'll try to trace it right now. Okay. The red graph is f of 2x. It's compressed. It squeezes the graph in. See how it kind of scrunched in a little bit? And then for a number between 0 and 1, a fraction, f of half x, the yellow one, it's an elongation. It's like stretching out the graph. And this happened a lot in trig, you might recall. In fact, a good example of these is what happened in trig. Like maybe I'll just go ahead and show you an example of that, because you might remember this from trig. And we have a whole chapter that we're doing trig later on. That super big chapter that we had. This is all trig. It's a review of trig. That's why it's so long. But I think the best examples of this are the ones that you had from trig, because you already remember your trig. So I'll show you this bullet. This one you want to put down in your cheat sheet. I don't think you need these last two. It's kind of combining 2 into 1. So you can survive with just this. The graph of y equals f of negative x is the reflection about the y-axis of the graph of y equals f of x. Okay. Remember, if the negative was outside, that's a reflection about the x-axis. I'll show you examples of each of those. Okay, so what do I think is worth putting on your cheat sheet? Maybe these two. Where am I? Top of 108. For c greater than 1, the graph of y equals f of c of x is a horizontal compression. For c between 0 and 1, it's a horizontal elongation. It stretches it out. And the graph of f of negative x is a reflection about the y-axis of the graph of y equals f of x. Okay, I'll show you examples of each of these in the remaining 10 that we have. I think I'll just show you trig examples. And we'll pick this up again when we get to trig. We call the graph of y equals sine x. Just focused here. Y equals sine x. One period, you might recall, looks like this. And we know it keeps going on and on. Sine of 2x, that changes the period, you might recall. So that sort of scrunches the graph in. The period would only be pi. So this entire up and down, I got to finish that whole thing within pi. It's almost like you have a spring. Imagine this is a spring, right? And you just kind of scrunch it in up to there. So that whole up and down business, I have to finish it just within this part here. So it will look like this. Y equals sine 2x. We'll get to this in trig, but the period of the regular sine function is 2 pi. The period of sine 2x is just pi. So imagine this is a spring. If you just kind of compress it, just scrunch it in, it would look like that, right? And then they were saying something about elongation. Let me show you the elongation. Instead of 2x, suppose I had sine of half x. The big hint is the way I drew it. So I start off with my same graph as this. Period is 2 pi. Y equals sine of a half x. That's going to take this. Imagine I'm taking this and just stretching it out this way. That spring just comes out. And in this particular case, we go all the way out to 4 pi. Period is 4 pi. So that whole up and down sequence doesn't get done until I get all the way out to 4 pi. That's going to look like this. So here's sine x. So sine 2x, imagine you're scrunching the whole thing up, right? Scrunch it in. In this case, imagine stretching it out. Take this thing and just kind of move it all the way out like that. And that's the effect of sine half x. And something similar happens for all the other functions. So that's what they're trying to say right here. But yeah, the most practical applications are from trig. And as we know. And this one, I don't think you really need. This is just a combination of these two. Okay, so I don't think you need this. But the reflection ones, yeah, let me show you that. Because the square root function is a good example of that. So just for fun, y equals square root of x. Now you should already be somewhat familiar with the square root function. Like this. If I put a negative in front of the whole thing, well, all the positives become negatives. So that's going to go like so. Reflect about the x-axis. Reflect about the x-axis. But what if the negative was underneath the square root? I'll show you that. And then the hint is the way I'm drawing it. Y equals square root of negative x. This is a little bit tricky because at first you might say, well, you can't do that because you can't take the square root of a negative. That's true. But actually this works if you plug in a negative. In fact, you're only allowed to plug in negatives and 0. That's going to go like so. So reflect about y-axis. See, this is real tricky because your first impression is saying, well, you can't do that. I can't take the square root of a negative. Correct. But if you plug in a negative, like if you plug in -1, right? You actually get something because then you're doing the negative of -1, which is 1, and the square root of 1 is 1. So for this expression, you're not allowed to plug in any positive quantity, but you're allowed to plug in negative quantities, right? See, I can't plug in 4, but I can plug in -4. Because what happens when you plug in -4, you would have -4, which is 4, and the square root of 4 is 2. Okay, so y equals radical x is this. Y equals square root of negative x reflects about the y-axis. Okay. So that's what they're trying to say right over here. All right, so we're just about out of time, but I'll leave it to you to figure out 23, but do the same kind of thing. So f of 2x, that's a compression. And f of a half x, that's an elongation. Okay, I don't really want to corrupt this picture, but imagine taking this graph and just shoving it in, so to speak. And then the negatives would just reflect across either the x or y axis as long as you do it the right way. Okay, but I see we're just about out of time, but we can go from there. Okay, but this 2x and that half x, same principle as here. Sine of x, sine of 2x, this is like you're squinching it in, but sine of a half x, you're just spreading it out. And then having a negative reflects about the x-axis. Okay. So I'll just talk quickly about 23 without drawing it. So f of 2x, this is going to squeeze in like that. Imagine if I would take these two, take this and just kind of squinch it in. Okay, so it gets scrunched in. The half x would elongate it, would make it spread out more. Imagine taking this and spreading them out that way. So f of 2x, squinch it in. F of half x, move it out. And then that one and that one will reflect about the y-axis. And there we go. Okay. So I see we're just about out of time. So schedule-wise, we are here. So I think we're right on schedule. So we have Tuesday, Wednesday, and maybe Thursday also, since this is a buffer day. Buffer day doesn't mean it's a holiday. We're still going to meet. But in case I don't finish everything from 2-5, I still have Thursday to do that. And Friday is going to be our next test. Okay. All right, folks. So that'll do it for today. Anybody have any questions? Let me check the chat. Also, I don't see anything in the chat. All right, so otherwise, that'll do it for today, folks. So anybody else with a question? All right, have a good day, and we'll see everybody next time. Okay, all right, bye, everybody.
Thank you, Professor.
For
Thank you.
the, I just wanted to confirm that for the negatives on problem, oh,
Yeah, I'm still here. Marissa?
yeah, sorry, I thought you left. I just want to confirm that for the negatives on 23, we reflect across the y-axis, right?
For 23, let me see. I don't know. What happened? Oh, here we go. Correct, you reflect across the y-axis.
Okay, perfect. Thank
Yeah.
you.
So like whatever you got for this one,
Yeah.
then just reflect across the y-axis for that one. And same thing over here.
Okay, perfect. Thank you.
Okay, you're welcome, Marissa. Okay,
Bye.
bye. Bye, see ya.